So how do we determine the exact mass of an atom? Well, one way is to use a mass spectrometer. That's an instrument that's extremely sensitive to mass. And here's how it works. A mass spectrometer, you take a sample and you ionize it. And by ionization, we mean stripping off electrons. In this case, we strip off all the electrons. The sample is then accelerated towards an electric field and directed through a magnetic field. Now, when charged particles hit a magnetic field, they're deflected by the magnetic field. And they're deflected according to their mass. Heavier particles are not as deflected as lighter particles. So you have this stream of particles, and it hits that magnetic field, and it's fanned out based on their mass. Here's a little animation that shows that happening. You take a sample, and you allow it to be ionized and accelerate it. It goes through the magnetic field, and it's deflected. Now, that was a relatively small mass. Let's look at a larger mass coming through the same system. We're going to ionize it. It's not deflected as much. So you have a distribution of masses that you can resolve using a mass spectrometer. So what the output of the instrument looks like is a mass axis that will tell you the mass of the particles that you injected. And there'll also be a vertical axis. And the vertical axis will tell us about how many particles there were. And that's very useful. Remember when we had our carbon, we said that 1 in 100 of these particles was a carbon-13. The other 99 were carbon-12. That's a difference of 1 mass unit. And you'd have a ratio of 100 to 1 of their peak heights, because you'd have 100 carbon-12s for every 1 carbon-13 entering your mass spectrometer. So let's look at a few masses. We have, for instance, what would show up at mass 1? Well, the only thing that has mass 1, a single proton mass, would be hydrogen, the hydrogen isotope with no neutrons in the nucleus, a single proton. If you look at mass number 2, that would be maybe a hydrogen molecule with 2 single protons making a molecule, or it could be hydrogen atoms of mass 2, deuterium atoms we call them, that have a proton and a neutron in the nucleus. So you can tell by the mass spectrometer, you can get the mass, but remember, mass does not determine the identity of the element. Certainly a clue, but it does not determine the identity. We need to know the number of protons in the nucleus to get the identity of an element. So, mass 3, that could be tritium, or it could be a molecule of deuterium and hydrogen hooked together to form a hydrogen molecule. And you can go through, think about several different things. Here at mass 12, we'd maybe expect that to be carbon-12. And at mass 13, carbon-13, if we injected some carbon into our mass spectrometer. And you can go on down the line. Here's oxygen-16. At mass 18, you could have a water molecule with oxygen-16 and 2 protons, 2 hydrogen atoms, or you could have oxygen-18, the isotope. And here's a few other examples. Oxygen-16, the oxygen molecules, and carbon dioxide. Mass 44 if it's carbon-12 and oxygen-16. But of course, it could be carbon-13 and oxygen-16, a slightly higher mass. So a mass spectrometer, exquisitely sensitive to mass. It's so sensitive to mass that you can determine, by using a mass spectrometer, mass lost during chemical reactions and the energy output that's due to relativistic mass loss. The E=mc² mass loss can be determined by modern mass spectrometers. That's how accurate they are. Incredibly tiny mass losses can be determined by this method. It's a beautiful instrument, and it's very, very, very powerful for measuring atomic masses.